Hey students, welcome back. Mr. Danahauer here. So now that we have learned how to draw atomic Lewis structures, we are now going to draw molecular Lewis structures. And again, remember atomic Lewis structures are simply showing where the valence electrons are in an individual atom. But a molecular Lewis structure is when we have more than one atom covalently bonded together. So sharing electrons, holding them together. And the purpose of doing this is to understand one, where are the bonds and what kind of bonds are they? And the molecular Lewis structure also helps us determine the shape of the molecule, which helps us to determine if the molecule is polar or not. So remember, water, right? H2O is a polar molecule, and that gives it certain properties like it dissolves a lot of things, or it has a high boiling point, some of these things. And so determining whether or not a molecule is polar or nonpolar starts with drawing the Lewis structures. So how do we draw a Lewis structure for a molecule? First, we are going to look at the formula. This is a first molecule. You should have this sheet in front of you and you can walk through this with me. We'll go through a couple of examples together, and then I'll have some practice for you to do individually, okay? Sorry if my camera goes in and out of focus here. So this is a covalent molecule. I know it's covalent because it has all nonmetals, and it's telling me in the formula there is one carbon, there are two hydrogens, and one oxygen. And because they're written all together, there's no spaces between them, I know that all of these are bonded together as one unit. They're one molecule. So in order to draw this Lewis structure, there are several steps, as you can see, that we're going to go through. The first thing that we're going to do is practice what we just did previously, and that's draw the atomic Lewis structures. The reason we're doing that is to determine the central atom, and that's the atom that all of the other atoms are bonded to, kind of like the hub of a bicycle wheel. So we're going to go ahead and say I have three types of atoms: carbon, hydrogen, and oxygen. And carbon has four valence electrons. You should be able to determine that quickly from the periodic table by now. And I'm going to put those around: one, two, three, four. And remember, we're going to follow the same rules we did before. If there's an empty seat, we're going to put electrons in the empty seats and put one electron on each side before we start pairing them up. So this is a good Lewis structure for carbon: one valence electron for hydrogen, and six for oxygen. So that's a good Lewis structure for the atoms. So that's step one. Step two, we're going to look and see which of those has the most unpaired electrons. Carbon has four: one, two, three, four. That means it can share or bond four times. Okay. Hydrogen only has one. Oxygen has two. So which one has the most places that it can share? That's carbon. So we can see carbon is the central atom. It has four unpaired electrons. Okay. Um, the next step is we need to determine the total number of valence electrons that are in this molecule. Well, how do we know that? Well, we come back up here to the formula, and for each atom, we're going to total up the valence electrons and consider how many of those types of atoms we have. This is one of the most important numbers that you can come up with when you're drawing a Lewis structure, because we have to determine the number of valence electrons that are in this molecule. So if we look at this right here, you can see I've listed out every atom in this molecule. You don't have to do it this way, okay? You can do shortcuts, but you have to come up with the right number of valence electrons. So carbon has four, and there's one of them. Hydrogen, each hydrogen has one, so one for each hydrogen. And then oxygen has six. So when we add all that up, we get the number 12. One thing I want to point out, your total number of valence electrons should always be an even number. If it's not, you did something wrong. You need to go back in and see what you did wrong. So if you ever come up with an odd number of valence electrons, try again. Go back and check, did I get the right number of valence electrons for each atom? And I accounting for all of the different atoms that are in this molecule. So like the two hydrogens, right? Okay, so that's next. So this number is going to come back to us a lot. We're gonna see this number quite a bit. Okay, now that we have the number of valence electrons and we know that carbon's a central atom, we can start drawing our Lewis structure. The first thing we'll do is, again, we're going to put, if you think about like a wheel, when you have a wheel, there's always something in the center that kind of holds everything together. We call that the hub or the center. And the central atom is the same way, in this case, carbon. It's in the middle, and we're going to attach everything to carbon. It's the central atom. So when we draw this out, we want to make sure we draw both hydrogens and oxygen and the carbon as the central atom. So I've sort of laid this out, as you can see. And now we're going to go ahead, and we know that these are bonded together. And so I want to draw a line showing that they're bonded. Remember, those lines are simply pairs of shared electrons. So I have a pair here, I have a pair of electrons being shared here, and I have a pair of electrons being shared here. The way that you place these around the central atom, where you put them doesn't matter, but we're always going to put them at right angles. So if our central atom is here, we can put one here, 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 and here. So the most you're ever going to have that are connected to the central atom is typically going to be 4. But if we have less, that's okay. And we could put these in any place at 90 degrees that we wanted to. So I could put the oxygen here and the hydrogens here. For our purposes, that doesn't really matter. Okay. All right. So now when I started drawing this based on the central atom and I bonded it together, I already included some of the 12 total valence electrons. How many of those did I use to make the bonds? I used 2, 4, 6. So I've already accounted for the 12 electrons total. I've already used up 6 in the bonds. All right. So I'm going to take the total, subtract the 6 that are in the bonds already, because I don't want to put too many on there. And now I know I have 6 electrons left that I need to place around. Now, I want to point out something. I'm going to stop, pause for just a second, and let you know when we draw atomic Lewis structures like this, okay, it's okay to have single electrons because it's just one atom. But when we draw molecules, the whole reason molecules form is to fill an atom's octet, to fill their valence shell. So we will never have individual electrons in any of our Lewis structures. They're always going to be in pairs. It's either going to be a pair that's bonded, or it's going to be a pair that's a lone pair, as we'll see in just a second. So now I need to come to my molecule here, and I'm going to place the rest of the 6 electrons around the atoms. Now, how do I know where to put them? First, we can't put them where there's already a seat taken up, right? Here, here, here. These are already taken up, so we can't put them there. But we also cannot put them on hydrogen. Remember, hydrogen can only take 2 valence electrons, and then it's full. And if we look at this, how many does it have? Right? If I circle those, it's sharing 2, so that counts for 2 for hydrogen. So these hydrogens are full once we once we bond them, and you're never ever going to do anything else to hydrogen. No extra bonds, no extra electrons, just one single bond. That's it. Okay. All right. Now let's come down here, and what I've done is taken the rest of the 6 electrons, and I can either put them on carbon because I have an open spot here on carbon, or I can put them on the oxygen. As a rule of thumb, I put all of my pairs of electrons that are remaining on the outside, so not the central atom, but on these atoms. And then if I have any left, I go to the central atom. That's just my rule of thumb. You can do it the other way if you want, but that's the procedure I follow. So what I've done is taken 6 electrons as pairs, treat them like shoes, okay? And they keep the pairs together. So there's 2, that's one pair there, 4, and 6. And now if I count up how many electrons do I have in this, I have 2, 4, 6 that are bonding, plus the 6 that I just put on, for a total of 12. And back up at the top, right? That's what we determined we needed, was 12 valence electrons total. Now remember, once you determine that, you cannot add or take away any electrons. We can only have 12 on this structure. So no, you always have to keep it 12. That's not going to change for our purposes in our class. All right. So now we have our structure. The last question that we need to ask, remember, why do atoms bond and form these molecules in the first place? To fill their valence shell. For hydrogen, that's 2. But for all other atoms, that is octet, which is 8. So let's check and see if all of our atoms have a full octet. We already said each of our hydrogens has 2, so the hydrogens are good, okay? They have a full outer shell. Oxygen here has 2, 4, 6 unpaired electrons and 2 bonding. So 6 plus these 2 gives me 8. So oxygen is happy, it's full. Carbon, though, look at what carbon has. I'm going to circle the ones that carbon has or sharing. It has 2, 4, 6. So it is not full. So what do we do to fill this up? What we're going to do is say, well, I know that the oxygen is full and it has some extra electrons. And instead of just hogging those electrons to itself, it's going to share those electrons with the carbon. So I'm going to take any of these pairs, just one pair, because that's how much makes a bond. And I'm going to move that into another bond. So now we have a double covalent bond between carbon and oxygen. If we look at what that looks like down here, right, we can see now I've taken the pair that was here and I moved them instead into a double bond. So let's recount now. We know we still have 12 valence electrons, 2, 4, 6, 8, 10, 12. Always count in pairs. But let's see if we're full. So we already said hydrogen's good because it's got a bond. We're not going to do anything else there. Now let's look at the oxygen, right? It has 2, 4, 6, 8 because each bond is a pair. So oxygen's good here. Let's look at carbon now. Carbon is all bonds and it has 4 and each one has 2 electrons, right? 2, 4, 6, 8. So now both carbon and oxygen are full. Now, I just want to caution you. Some of you are going to get bond happy, and you're just going to start putting double and triple bonds on things and skip this procedure that I've given you. Don't do that. Okay, that's one of the biggest mistakes I see is people trying to put double and triple bonds on before they've counted and figured out if we need any double or triple bonds. The only time we need to add extra bonds is if one of the elements is not full, if it doesn't have a full octet. So that's how we get to this Lewis structure, and this is a good Lewis structure for this molecule. Let's go ahead and move to another molecule. This is one of my favorite molecules. It is called ammonia. And I think it's fascinating because this is one of the main ways that we make fertilizer from ammonia. You might remember NH4 plus, which is ammonium. That's one of our polyatomic ions. So ammonia is similar to that, but it doesn't have a charge, so it's not a polyatomic ion. All right, now let's go through the process again. I'm going to pick up the pace a little bit here. First, draw the atomic Lewis structures for each atom. I have nitrogens and I have hydrogens. I don't need to draw 3 hydrogens. That's a waste of time. So I'm just trying to figure out the central atom here. You already could tell me that hydrogen is never the central atom because it can only ever share one time. And that's a good thing to remember. If you only have an atom and hydrogens with it, then you know the other atom is a central atom because hydrogen is never the central atom. So let's go ahead and determine periodic table for valence electrons. Nitrogen has 5, so 1, 2, 3, 4, 5. Right? It's okay to have single electrons when you just are drawing an atomic Lewis structure. Hydrogen has 1. Let's go ahead and figure out what's a central atom. We know it's going to be nitrogen because it has 3 unpaired electrons, 3 places that it can bond. Hydrogen only has 1. Okay. Now, I'm going to jump down here to step number 5, right? Because this is the process I go through. Once I figure out the central atom, I'm going to put nitrogen as the hub, It's the central atom, and I'm going to bond my three hydrogens around nitrogen, right? That these are all bonded together, and I know nitrogen is a central atom, and I know that there's at least one bond for each hydrogen to nitrogen. Okay, so that's where I go next. Once I know the central atom, I draw the initial structure down here. So we're going to skip this one because we just did that. So back up here now. All right, we know nitrogen is a central atom. Let's add up the total number of valence electrons. I'm going to do a different format over here. You can do it however you want. I know I have one nitrogen, and that is a total of 5 valence electrons. I know I have 3 hydrogens, and they each have 1. So 3 times 1 gives me 3 for a total of 8 valence electrons. Okay. Now again, check to see, is this an even number? That's just one error check you can always do. And because it's an even number, that gives me confidence that I did this right. So I'm going to carry that number down here just so we can see it. 8, all right? And I'm going to come over here and say, okay, I know I just used up some of those 8 valence electrons to make these bonds, all right? I have to have at least one bond between each atom and the other ones. So that's 2, 4, 6. And how many are left? 2. So I've got to put those 2 electrons somewhere. Let's go ahead and move down to step 6. Sorry, step 7. And I'm going to go ahead and go nitrogen, hydrogen, hydrogen, hydrogen. Guys, as we move forward, we're really breaking this down into individual steps, but as we move forward, we're going to combine some of these steps so it goes a little faster. Okay, so I have 2 electrons I have to place, 1 pair. Okay, they can't go on hydrogen because hydrogen's done. Remember, we're never going to touch hydrogen. Once you put a bond to it, it's done. Now, the only place that can take a pair of electrons is on that empty spot on the nitrogen. And that covers all my electrons. So let's count them up. I should have 8 total, and I have 2, 4, 6, 8. So that's good. All right. Now, last check. Do we need any double or triple bonds? So I'm going to look. Each hydrogen has 2, right? So all the hydrogens are good. And let's see, how many does nitrogen have? Nitrogen has 2, 4, 6 that are bonding, plus this lone pair, and that's 8. So this nitrogen is full. It has 8 electrons. And that means that this structure is done. We do not need to put any double or triple bonds on here. Okay. If everybody's full, no extra bonds needed. So that's a good Lewis structure for the ammonia molecule. Okay, on the back of your paper, we have some more practice problems. So flip it over and let's try some of these together. So again, on those 2 last examples, I really went through, and did most of the steps there. But I'm going to consolidate and just kind of show you a little bit faster way to do these. We're still going to do all the steps, but we're going to combine some things together. Okay, so first, step 1, right? Let's just look and see what we have here. This is phosphorus tetrafluoride, and I have 1 phosphorus atom and 3 fluorine atoms that are all bonded together. First, before I can start my molecule, I need to see what the central atom is. So I'm going to go phosphorus has 5 valence electrons, just like nitrogen did in our last one. And fluorines have 7. So it's going to look like this. All right. So central atom is the one with the most unpaired electrons. Phosphorus has 3, and fluorine only has 1. And a quick trick: most of the time, not always, most of the time, when we write the formula for a molecule, we remember in ionic we always put the nonmetal first, right? Well, in covalent we oftentimes put the central atom first in the formula. So if you're not sure, which I'll show you in a second, an example of like how would we not be sure, I'll show you in a second, but this one is I could say that's probably the central atom because it comes first, and I confirmed that by drawing the Lewis structure. It has more spots for bonding. So let's draw our initial structure: phosphorus with 3 fluorines around it. Again, it doesn't matter how you put your fluorines as long as they're at right angles to the center. All right, so I got my initial structure here. Now we need to figure out valence electrons. So I have a phosphorus, one phosphorus, and that has 5. And I have 3 fluorines, and each fluorine has 7. So 3 times 7 is 26. Just kidding. 21. Okay. So 21 plus 5, looking for an even number, and we got one. So 26 valence electrons, right? That's the total we have to have on the final Lewis structure. So let's go ahead and see. Now I'm going to show you a different technique for getting your valence electrons on here. I never, in the way I do it, I showed you differently, but the way I do it is I just start at 0. And once I have my structure on here, I start at 0 and I count up to 26. So let me show you what that looks like, okay? I need 26 total valence electrons. I already have 2, 4, 6. And now I'm just going to keep counting and putting them in pairs where there's spots. So here's my process. 2, 4, 6, 8, 10, 12, that's full. 14, 16, 18, that's full. 20, 22, 24, that's full. There's only one last place I can put my last pair, and that's on this empty seat on the phosphorus. So now I put 26 on there total. Okay. Right. So you can do it that way, or if you like to go, you can do it this way, 26, and you've got 3 that are bonding. So we're going to subtract 6 total. I'm sorry, 3 pairs that are bonding. And so you have to place 20 on there. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That works too. Okay. Either way, I just think it's faster to count up from 0. Now let's count each fluorine. Now we need to see if everybody has a full octet. Is everybody happy in this molecule? All right, so let's see. Each fluorine has 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. So all of our fluorines are good. And if I count phosphorus, right, 2, 4, 6, 8. So it's good as well. So all of these atoms are full. I have a total of 26 electrons. So this must be a good Lewis structure. Let's try our next molecule here, which is sulfur trioxide. 1 sulfur, 3 oxygens. Step 1, draw the Lewis structures. Okay, sulfur has 6 valence electrons. Oxygen has 6 valence electrons, so their Lewis structures look very similar to each other. Right now we come to a problem, right? This is where, okay, sulfur has 2 unpaired electrons, 2 places they can share. Oxygen has 2 unpaired electrons. They have the same amount, so how do I decide which one is the central atom? Well, I'll come here and look which one comes first in the formula, and that's sulfur. So because that came first, I'm going to use that as a way to know which one's the central atom, or the hub of this molecule. I'm going to go ahead and draw the structure. So S, right? O, again, doesn't matter where I put my 3 oxygens as long as they're at right angles. Okay. All right, and now and let's figure out valence electrons. So each sulfur has 6. So I have 1 sulfur, and that's 6. And each oxygen, I have 3 oxygens, and each one has 6. 3 times 6 is 18, for a total of 24 valence electrons. So now I'm going to use my technique again, where I just start at 0 and count up to 24, making sure I count the bonded electrons here. Ready? 2, 4, 6, 8, 10, 12. That oxygen's full. 14, 16, 18. That oxygen's full. 20, 22, 24. All right, good. So I've got all 24 electrons on there. Again, I want to point out every electron I'm putting on here is paired. Some of you are going to go around and do stuff like this, where you do 1, 2, 3. No, always put it in pairs, because we know they're going to be paired up. So think shoes, right? Always keep your shoes in pairs. You don't want to have an individual shoe out there, or else you look weird walking around. Okay, so let's go ahead and now, last step. Let's see if this is a good Lewis structure. Does everyone have a full octet? All three oxygens look the same. They have 2, 4, 6 non-bonding electrons, and then 8 with the pair. So all of our oxygens are full. But our sulfur here is not full. How many electrons does it have? 2, 4, 6. So we have a problem, right? Sulfur is not full. How do we fix it? We are going to find one of the neighbors of sulfur that has a non-bonding pair, so a pair that's hanging out by themselves, and we're going to move that into another bond. Okay. Now, how do I know which one to use? In this molecule, it doesn't matter. You can pick any of them. Truly, that bond, the double bond we're going to make, resonates. It actually bumps around, and these electrons actually get shared more by all of them. But you don't need to know that right now. I just think it's kind of interesting chemistry stuff. So we're going to take a pair. I'm just going to pick this one and say that pair is going to move into a double bond right there. That pair is no longer on the oxygen. It's being shared between the oxygen and the sulfur. So when I draw my final structure, it's going to look like this. All right, you can see how it's going to look. This oxygen is going to have those, and then a double bond here with an oxygen, but this one only has 2 lone pairs on it. So that's a good Lewis structure for sulfur trioxide. Okay. If we go back in and count this up, do we have 24 valence electrons? You should do this every time you're finished and you're like, yep, I'm done. Here's what you should check. Just like in math when you plug X back in to see if it works, right? So 24, let's count them all. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I have 24 valence electrons. And if I count, I know all the oxygens are full. I didn't mess with these at all. So the sulfur has 2, 4, 6, 8, and this oxygen has 2, 4, 6, 8. So that's a good Lewis structure. Do I have the right number of valence electrons? And does every atom have a full outer shell? Okay, let's move on to the next one, silicon dioxide. So we're going to go ahead and draw our atomic Lewis structures for silicon and oxygen. I have silicon and 2 oxygens. So silicon has 4 valence electrons, and they're all singles, right? So it has 4 spots for sharing. We already drew oxygen in our last one, and we know that it has 6 valence electrons, so it only has 2. So our central atom is going to be the one with the most unpaired electrons, and that's going to be silicon. And like I said, that comes first in the formula. So let's go ahead and draw that down here. Silicon and oxygen. It's going to look like that. Okay, 2 oxygens, 1 silicon. Count up valence electrons. Silicon has 4, and the 2 oxygens each have 6. So 2 times 6 is 12, and we have 16, which is an even number. It's good. So let's go ahead and count from 0 up to 16 in pairs. We have 2 in that bond, 4 in that bond, 6, 8, 10. That oxygen's full. Let's come to this one. 12, 14, 16. Okay. Now we've got all the valence electrons on there, but is everybody full? This oxygen right here has 2, 4, 6, 8. So it's good. This is the same, looks exactly the same. So it's good. What about this silicone here? Okay, silicone only has 2, 4 electrons. It wants to have 8. So we're going to need to do some sharing from neighbors. Now, this presents a couple of options. We could share a pair from this oxygen and then another pair from this oxygen and make a triple bond. Or we could share 1 pair from this oxygen and make a double bond, and 1 pair from this oxygen and make a double bond. Honestly, either way I would accept as a correct answer, but the correct way is to put a double bond on each side. So one rule of thumb is nature likes symmetry. So we're going to keep it symmetrical instead of lopsided if possible. And so we're going to go ahead and go, okay, I'm going to take this pair, and oxygen, you have to share because silicon's not full, it's not happy. So share your goods, okay? And then we're going to do the same thing with another pair. Because why am I doing 2 pairs? Because this brings silicon up to 6, right? Silicon has now 2, 4, 6. When I take that pair off oxygen, and now I need to get to 8. So we got to 6. I need to do another pair And now that brings me to 8 on silicone. Oxygen's still sharing those, so it counts for oxygen. It just doesn't get to hog them, it has to share them. So when we draw our final Lewis structure, it's going to look something like this. Okay. And actually, this is actually a linear molecule, so I should have drawn them at like 180 degrees just to show you. But you don't need to worry about the shape. That's something that in our class, I'm just going to tell you what the shape is. So that does have a really big impact on the properties of the molecule, but we're not going to worry about that. That's for chemistry class. Let's do our last one. This is hydrogen cyanide, super special molecule used in the past to bring people to an untimely death, I shall say. But hydrogen cyanide is poisonous. You definitely don't want to ingest any of that or you will quickly die. So anyway, this is a very simple molecule. It's made of one hydrogen, one carbon, and one nitrogen atom. So we're going to draw some quick Lewis structures for these to determine the central atom. Remember, hydrogen's never the central atom. Carbon has 4. If you ever have carbon in a molecule, you can be pretty sure that it's the central atom, and in this case it is. Nitrogen only has 3, so we're going to put carbon in the center and then bond hydrogen and nitrogen to that. This is a really good example where carbon is a central atom, but it doesn't come first. Focus. Hold on. Focus. Come on, focus. Okay, there we go. Just having trouble focusing. So hydrogen comes first in the formula, but it's not the central atom. Water is the same way, right? Water is H2O. Hydrogen comes first in the formula, but oxygen is actually the central atom. So always draw the Lewis structures to determine the central atom. But if you can't tell from the Lewis structures, you can look at what comes first. Then this one, we can tell carbon's in the middle. So I'm going to draw carbon, nitrogen, and hydrogen. Number of valence electrons, carbon has 4, nitrogen has 5, hydrogen has 1. We only have one of each of those, so our total is 10. And again, it's an even number. Okay, so how many do we already have on this molecule? 2, 4. I can't put any on hydrogen. It's done. Don't touch hydrogen. Once it's bonded, it's happy. And if you add more, it's going to become unhappy. So 2, 4. I'm going to go to nitrogen, 6, 8, 10. Okay. Can't put any more on there. Can only have 10. Now I've got to figure out, am I full? Is everybody full or not? Hydrogen's none. Already told you that. Okay. Nitrogen has 8, 2, 4, 6, 8. So it's good. Carbon only has 4. So we're going to have to do some sharing. The only one that can share electrons to carbon is nitrogen. So I'm going to take one pair and put it as a double bond. So now we have a double bond. That brought carbon up to 2, 4, 6. I still need 2 more. So I'm going to take another pair from nitrogen and move it into what we call a triple bond. We haven't seen that yet. Okay, that's the most bonds you can have. There's no quadruple, like 4 bonds. It's either 1, 2, or 3. All right, so this triple bond now brings carbon up to 2, 4, 6, 8. This nitrogen now has 2, 4, 6, 8, and the hydrogen has 2. Everybody's happy. It's a party. This is a good molecule. All right. And our final structure looks like that for hydrogen cyanide. Okay. So that's how you draw these. I'm going to give you some more practice problems here. And I do have a video that goes over those as well. So if you need to walk through those with some extra help, you can use that. But I would encourage you to try it without using the video for now and just make sure like you're getting these steps down. And please check as you do these, check the key that's circulating around so that you can make sure that as you complete one, you're doing it correctly and you're not developing like bad habits as you're doing these. Okay, thanks for watching, guys. Hope you have a great day and Sko Ridge.